Hi there, I'm Fred Major. I have a background in aerospace and missiles. I started way back in 1957, and we were started out with the intercontinental ballistic missile called the Atlas missile. And through the years we've done wondrous things, which is the background of the aerospace industry. And what's very important is the fact that we developed technology that wasn't taught in school or colleges and so forth at the time, because it was all newly being developed. The big difference is that in those days, a rocket motor carries its own oxygen, as opposed to a jet engine takes the oxygen out of the atmosphere. So when it carries its own oxygen, you can't carry oxygen very well unless you can liquefy it. Now it's at a density where it's practical to transport. And when you liquefy oxygen, it's minus 296 degrees Fahrenheit. That's pretty cold. You're probably more familiar with liquid nitrogen, which also is approximately the same temperature. Since oxygen and nitrogen will make up our atmosphere, those two gases liquefy at about the same temperature. Now, when you're operating at temperatures like that, how do you work with those? And that's the thing that was the big challenge for us in those days. And we had to create new structural equations, we had new temperature equations, and we had to learn how to work with these very cold gases that you had to use to go to out of the atmosphere. Because once you get out of the atmosphere, the only way you can burn the fuel is to carry your own oxygen with you. So that's my background, and what I really want to talk to you today a little bit is about engines. In 1988, we won a contract from the U.S. government, DARPA agency, which is the developing agency for all new technology for the U.S. government. The challenge was to see if we couldn't come up with an engine that was 50% efficient. Now that doesn't sound like much, but let me tell you, the most efficient engine built and operating today is only 30% efficient. What does that mean? It means that you're only burning about 30% of the fuel. The rest of the fuel is exhausted through the engine, through the exhaust pipe, into the atmosphere, and that's what causes pollution. The fact that you have unburned fuel going into the atmosphere. So it's just being vaporized into the atmosphere as we operate our vehicles, trains, buses, aeroplanes, everything. That's the most efficient engine ever built, is only 30% efficient. So the target was to come up with one which was 50% efficient. How do you become more efficient? Now, you probably have heard about super carburetors and something over the many past years, and that's all folklore and wishful thinking. Had nothing to do with efficiency. The only thing that increases efficiency is burning more of the fuel. And the only way you can burn more of the fuel is to have more oxygen available to burn. Now, in our atmospheric conditions, normal atmospheres that we have around us today is roughly around 14.7 psi. That's an atmosphere. So what we do is we try to condense the atmosphere, squeeze it down, and get more oxygen. Now, in our oxygen, we only have 22% of the oxygen is oxygen. Only 22% of the atmosphere is oxygen. The rest is nitrogen. And nitrogen doesn't burn. So we've got to compress it to get more density of oxygen so we can burn more fuel. Now, a good example of what that is how do you put out an oil fire? How they put out an oil fire is they use dynamite. And the dynamite explodes, uses all the oxygen that's in that local spot, and the fire goes out. Another example is hydrogen. Hydrogen is very volatile and probably one of the best fuels around. Biggest thing is very hard to transport. So during the heyday of the Zeppelins and so forth, since they didn't have helium in Germany and other parts of the world, they do here in the United States, they use hydrogen. That was a light gas, and that's what they used. And when the Hindenburg came over and it caught fire, it didn't explode. It burned and burned and burned. And the reason why it was burning so slowly, because it almost put itself out each time. It almost used all the oxygen that was in the local spot, and then it almost go out, and then some oxygen would be available, and it would burn a little bit longer. But a true hydrogen fire, if it has enough oxygen, would act like an explosion. In the missile industry, to give you an idea, we used to give examples of this. I take a piece of clean stainless steel, absolutely as clean as you can get it, and I press it with my finger, and the oil off my finger, I put a drop of liquid oxygen on that, and it would explode. It would explode like a cap gun. Pop! It would do that. So when we were building the missiles, in order to put liquid oxygen inside, it had to be extremely clean. We used to call it LOX, or liquid oxygen clean, and it had to be put in clean rooms, because any oil, anything whatsoever like that, would cause the fuel to actually burn. So that's kind of a little bit of my background. Anyway, we started to build this engine, which was 50% efficient. Now, what do we have to do is we got to get more oxygen. And any engine designer knows to get more oxygen, you have to take and compress the air. And how do they compress the air? With an air pump. Now, in the United States, we make it very fancy. We call it a supercharger. It's an air pump. If you're in Germany, they call it a compressor, which it really is. It's a compressor. If you buy a Mercedes car today, you'll see it has compressor written with a K. But that's just to let you know that they've got a compressor on board to compress the air to get a little more oxygen when you're burning the fuel in the engine. The only problem is that the engine is really a pressure vessel, and it's a very, very poor pressure vessel. If you ever looked at a air compressor, the tank for the air compressor is a cylinder, and the ends are sort of hemispherical, and that's absolutely necessary to have a pressure vessel. Now, if you take that same pressure vessel and you disconnect one end and put a piston in the end, and the piston moves up and down that cylinder like an engine does, it doesn't see the stresses because it's a movable structure. It moves, and it doesn't tie to the sidewalls. The other half is the head. Now, the head is bolted on to the end of the pressure vessel. But the stress in a pressure vessel is directly proportional to the radius. The bigger the radius, the higher the stress. So it works pretty much whether it's a pressure vessel or a bridge or anything like that. If you're going to build a bridge, you have a surface like this and you're trying to support it, everyone knows you build an arch. And the arch is that radius, and that radius is what supports it. Now, you can go like the Golden Gate Bridge, and you build it up high, and you put